Okay, I guess I'll get started. So on Thursday, we left off, we finished with the introduction of the Gaussian instrument. Okay, so I calculated these Gaussian Krauss operators. Are there any questions about them? I ended with this funny point about, I keep saying universal, universal. These Krauss operators are universal. And at this point, I pointed out that, statements like 1 equals sum over x, omega x dagger, omega x are universal expressions. You don't have to specify anything about the spectrum of this operator x in order to see this statement. Okay? Just the properties of exponentials gets you there. Okay? And this is going to mean something once we start doing multiple observables. Yeah. So we'll return to this over and over again, but this is the first flavor of what I mean by universal. Rob. Yeah.
No, I think you answered it.
Okay.
Maybe the comment was that I'd kind of like to see why that's true, kind of more
Sure.
just in the mathematics. How is it?
Okay, so we're about to calculate the decoherence channel. So I think that'll do everything, because once we get that, we can show it's trace preserving, etc. Yeah. So great. Indeed, the next thing to do, well, before I proceed, are there any other questions? Okay. I can hear you, Kevin. Yeah. Oh, yeah. No, dx is just the measure on the real line. Yeah. Well, thank you. Are there any other questions? Alrighty. So yeah, to get a sense of what's going on, let's calculate the decoherence channel. So what is the decoherence channel, right? Z sum on x, omega x, O dot, omega x dagger, right? Where remember, this O dot notation, I use it quite a bit. I get it from Carl. Apparently, he gets it from Chris Fuchs, and Fuchs doesn't like this notation anymore, but he insisted on it 15 years ago. So here I am using the O dot. Okay. Okay, so let's just crank it out. So of course, this is just integral dx over 2 pi sigma squared e to the minus x squared over 2 sigma squared. Okay, these guys. So actually, yeah, okay, I'm going to put a parenthesis. So e to the minus theta squared, x squared, O dot, e to the minus theta squared, x squared. Oops, I put the wrong piece in there. Oof. Please forgive me. Of course, I want the x bits to just be in the integral. So one of the points I'm making here, right, is the second term, this quadratic bit in the exponential. Where's my eraser? Doesn't have any little x dependence, right? Okay, and I like to put a little circle to mean composition of superoperators. Does everybody understand what I just wrote? It's a little, normally you don't write these like a, this is not a matrix, right? I'm just fitting thing O dot thing. At this point, everything commutes. There's nothing in here that doesn't commute. So you don't have to worry too much about stuff. But technically, these guys go in here, right? Okay. So I'm going to do a little blackboard magic. Okay, just, is everyone okay? Yeah. So this guy, what is that? Well, I can write him as x o dot 1 plus 1 o dot x. Okay? Right. Similarly, I can write this guy as e to the minus theta squared. X squared o dot 1 plus 1 o dot x squared. Okay, so then what I see, right, is this Gaussian integral. So I know off the back of my hand the statement that, so this thing on the left, right, is, this is just a normalized Gaussian distribution, right? And if I put in a e to the x any a, right, then this is just e to the 1/2 a squared sigma squared. Okay. This is something I just have off the back of my mind. These exponentials, when you Gaussian expect them, you just get a factor of the variance in the exponential. Okay. If you prefer, you could like write a ax squared right here. Okay, so I'm just going to do that here, because again, everything commutes. So I can just do that. So what do I get? E to the, now I'm going to make mistakes, so I need you guys to help me not make mistakes. But I think so far so good. Okay, that's that one. And then we've got this guy. Plus 1 o dot x squared.
So you had the square root below the x on the first line, I guess?
Yeah, oh right, this is supposed to be a normalized Gaussian distribution, yep. Yeah, in my head again, I'm like, oh, it's just a Gaussian average, so indeed I wasn't paying too much attention, but that's how you, I was just saying I forgot a factor of sigma squared. Of course, I parameterized everything so that they're in units of sigma, so sigma is going to go away pretty soon.
Chris, the step you started with, where you have the curly braces.
Yeah.
That step. That from there to the thing below. Is there an easy way of seeing that besides just Taylor expanding each of the things up top and then collecting terms?
Yeah, I guess I think of it as like a o dot b. That's the same thing as a o dot 1 composed with 1 o dot b. Because yeah, okay, and then yeah, then this is, so then e to the x o dot 1. That's e to the x o dot 1.
Yeah, I guess that makes sense.
That one's a little easier to just, the 1 is coming along for the ride, right? Because x squared o dot 1, that's just x o dot 1, circle x o dot 1. Right. You can just keep going.
Okay. Okay.
Okay.
Yep.
Okay, so just using the tensor product, not using any spectral information about x in case that's what you're sniffing for. Alrighty. Any other questions, comments? Where are we? Okay, so this guy, so the sigma squareds cancel, and basically you get a couple factors of x squared, but then the cross term flips the sign. So this is just e to the minus a half theta squared x o dot 1 minus 1 o dot x squared. Okay? Can you guys see that? Like if I expand, so I'll insert. Right, like this whole thing, if I include the factor of a half as well, that's just 1/2 x squared o dot 1 plus 1 o dot x squared plus x plus x o dot x. Okay. So then this just flips the sign of this, which turns the sum into a difference. Okay. If you like Lie groups, this might be exciting to see because this thing is what's called the adjoint representation. Okay. So I'm going to call that ad sub x, right? In other words, it's the commutator superoperator, right? So yeah, the usual definition is add x of, say, rho is commutator with. Oops. You'll see why I'm so used to putting a square on the left and a round on the right. Okay, so then I'm just going to call this e to the minus theta squared half add x squared. Okay. So this is a special case of something called a dissipator or a Limbladian, and we'll talk about that in a moment, in case you're wondering. Alrighty, so again, I'm going to emphasize we didn't need any spectral information to do this calculation. Okay. So now let's verify the completeness relation from this. So,
sorry, what's it called again? A dissipative? What's it called again? A dissipative?
Oh, this thing, yeah, is, and we'll talk about this more, but I could denote this by dx, where this is the dissipator. Yeah, so like Michel Devoret uses the term dissipator.
Something about Limbladians as well.
And it's the same thing as a Limbladian, except in this case, the Limblad operator is Hermitian. But again, we'll return to this. Okay.
Can you remind me the lowercase ad?
Yeah, add.
What word does that stand for?
Adjoint representation. Yeah, not to be confused with Hermitian adjoint. That's the funny thing in group theory. Conjugation and adjoint are incredibly overloaded words that mean all kinds of stuff. Yeah, so adjoint representation. Adjoint is in fact Lie's word. The point is that Lie algebras act on themselves. And yeah, so the adjoint representation is exponentiating these. Yeah. You don't need another vector space to start thinking about moving around with the Lie algebra because it acts on itself. Yeah. Why he called that adjoint, I don't know. I can't. But he did, and we still do. Yeah. Any other questions?
So,
Yeah.
yeah, sorry, I'm just trying to understand what this tells us. So
What is what? Oh, yeah, what it tells us, yeah.
So this channel that you just calculated, what does it mean?
Oh, so if this measurement happens and you don't know x, so like another term for the channel is the non-selective operation.
Okay.
Right? So if you don't know what x is, the best thing you can do is average over all of the selective outcomes. And that's what this thing is doing.
Okay.
So it's called the channel because, in communication, what you want is to produce the same thing that you put in. So this is how much, essentially, the state after it's gone through the channel is different.
And does it act on the environment and system or only?
Oh, so yeah, that's a good question. So in communication language, X would just be called the environment, right? So for us, X actually is the observer. So and the observer is, I don't know how to say that. Oh. So I always think the system is not available. It's only these X's that are available, and then the theory. Did I answer your questions?
Yeah, and in this final form, like the exponential of theta squared and joint square law, what does it say? Like the fact that it's this exponential?
So, I mean, maybe one thing that'll answer your question is how the completeness relation follows from this. Okay, so like, what does it say? Whenever, I guess, I like to draw this diagram. Rho goes through this measuring device, X gets registered, and out comes omega X rho omega X dagger. But indeed, if X wasn't available, then, so if I maybe put a question mark there, right, then out comes Z of rho. Okay. Does that answer your question?
Yeah.
Okay.
I was just thinking like the shape theta square AD square X. Like, yeah, like if.
Well, we're going to start doing sequential measurements, and I'm going to start making conclusions about what theta has to look like,
Okay.
which is related to what we were talking about Zeno in a moment. So there's no Zeno in diffusive measurement because of how time works in sequence. Yeah.
Okay.
So we'll do more stuff with this. We're not going to move on from it. We'll do a few things with it.
At present, theta is a parameter that,
Theta.
instruments. Yes.
Yeah. Theta was basically the interaction strength. So it's pretty trippy. So yeah, let me dwell on this for a moment because it is important. Yeah, so remember that the interaction unitary in this case was e to the minus I 2 sigma over h bar p meter tensor x system theta. Okay, so of course you guys might have noticed, right, after I did this calculation, I'm dropping the system subscript. Okay, but if we're going back to the system meter, then this was the interaction. And so theta, no worries. Okay. Yeah, so theta is the interaction strength, which you usually think of as proportional to time. But once we start doing sequential independent measurements, it's going to turn out theta is the square root of time. Yeah, and then we're going to have to do some stochastic calculus.
I have another question. Can you move that forward up?
Of course.
So, in the limit that sigma becomes large, I have one intuition that says this measurement should give me like no information at all because.
Well, that's exactly where this point about time gets subtle. Yeah. So I'm going to think of theta becoming small.
I'm not talking about theta anymore. I'm on sigma.
Well, you said sigma large, and I think, oh yeah, that's the same as theta small, but
But sigma is different from theta. Those are two different
I mean, they are,
terms.
but okay. I'll just try to tune into what you're saying. So you want to consider sigma
I mean, I'm not
large.
mistaken, but I thought theta and sigma were two different parameters which I can vary independently. Is that correct?
Yes, but they're going to get clumped together pretty soon.
Okay, but for the moment, they're independently variable.
Fine.
So I wanted to just test whether that final result you wrote down made sense.
Yeah. Sigma went
Regarding
away.
limit of large sigma. So all sigma dependencies dropped out at this stage. And this
Right.
is not a identity transformation, right? So something has happened to the state.
Oh yeah, and that's that's
And yet-
because
Yeah, I mean, maybe you can tell me that perhaps I should think of it, no matter how big sigma is, but I'm getting increasingly weaker measurements, but nonetheless.
no, and you're not
Oh, you're not.
because I put a sigma here. Yeah, so I'm actually theta is like the strength in units of sigma. So it's like what this is doing is saying if like your meter state looked like this, right, then theta is basically how many of these the thing gets displaced by. Okay, and so if I increased sigma, then these guys would still have just the same overlap. So theta is just measuring this. So it doesn't become weaker and weaker
I see.
because I put a sigma up here. Yeah. So theta is sort of the part, theta is more in units of overlaps of the Gaussians, yeah. So that's indeed, it's taken me years to bookkeep it this way. These are exactly, yeah. Are there any other questions or concerns? Okay, so yeah, there's no sigma left over precisely because I put one up here too. Yeah. Okay. Whew. So what are we doing now? Let's see, I calculated the decoherence channel. And now, we were going to verify the, eraser.
It's right over there.
I got one here too. Thank you. So we're going to verify that it satisfies the completeness relation. So I'm going to use, I guess that means I have to use a certain notation. So basically what I'm doing is showing that Z is in fact trace preserving. Okay. So yeah, just to repeat, we found that Z is e to the minus theta squared half add x squared. Okay, and then the basic point is that So, right, what is trace? I can think of trace as trace of B dagger A as a Hilbert-Schmidt inner product, right? And so because of that, I guess what I'm saying is that trace of 1 Z of rho should equal rho, trace of rho. And of course, this trace technically has a Hilbert space, but I'm not using all of the, I'm just using this property of the adjoint. Gosh, I didn't prepare this part. I'm trying to explain why this is true.
What is that notation mean where you write the I in brackets on the left of
Yep.
edge?
So then this thing I would call 1 faux z of rho.
Just like
Okay. So I'm basically contracting. So z acts on rho, and then there's this adjoint action.
even the notation you set up for the Hilbert-Schmidt inner product.
Absolutely.
You'd be writing parentheses 1 bar C of rho close parentheses.
Yeah, there's no, and it's okay. Because that means something else in our notation. So like, okay. I guess I need to talk about this. So, for example, if we think about the operation, okay, kx o dot kx dagger, then ox of rho is put rho in the middle, but ox bracket rho, okay, actually means think of this like this. So this would be this guy acting in a different way. And this is just me and Carl. Okay, so this would equal this, okay, which is not the same operator. Okay. After a couple more classes, we're going to move on from Krauss operators and start working with frame operators. And there's these crazy relationships between the two. Yeah.
So I agree with the difference of those two things.
Okay.
I wasn't proposing to put a bar between your xi and your rho. I was rather saying you should write open parentheses 1 bar xi of rho close parentheses at the bottom left there.
What are you calling xi?
What is that, a zeta? The curly...
Oh, z. Math cal z is what
So yeah, I would have expected the Hilbert-Schmidt inner product between the identity operator and the operator that is the image of rho under z to just be, written as this kind of rounded direct notation.
Right.
1 on the left and z
Right.
rho on the right.
However, so like in this case, right? So what would 1 ox mean?
So
No.
Oh.
1 ox of rho close parentheses.
1 ox.
Right, of rho. So we're not taking, like, the things that appear in the Hilbert-Schmidt inner product are operators, not super operators. So I don't want an ox or a z appearing inside that.
So you're happy with this part?
Yeah.
That one's okay?
Yes. And
Okay.
so here's what I'm saying. If I take that expression you just put walk around, yeah, and I interpreted it as an instance of the expression above, where B is equal to identity, and A is equal to the operator that is the image of rho under Z. A is all of that.
Yeah.
And I should be able to write another.
Absolutely.
expression,
Yeah.
which is 1 bar Z of rho.
Yep.
Okay.
Agreed.
Good. So that so far that's good.
Yeah.
Now the difference with what you wrote upstairs is that AD of X is not an operator; it's a super operator. It's still waiting for something to happen.
Yeah.
Okay, so now I'm still puzzled.
Okay.
I
Great.
have a lot more clarity on what your
Nice.
notation means, but I'm still puzzled by that top
Excellent.
right notation. And
Excellent.
I'm still puzzled a little bit about what you wrote in the bottom left-hand corner because I still don't know what that notation means.
Okay. So I think I know what to do now. Okay, so I'm going to erase these funny examples. And
the much more simple-minded question. Your rounded Dirac operators,
yeah.
they're supposed to be the super operator analog of Dirac brackets. That's where I've seen rounded Dirac before. Okay.
Yeah. And there's almost no agreement about how to do that.
Right.
Yeah. Yep. Okay. But focusing on what Rob is saying, so I'm going to then explain the Hilbert-Schmidt adjoint. Okay. So So this is the same equation as this, and I'm going to say what double dagger is.
Okay.
Okay, so of course, a double dagger is going to be, by definition, so we've got a Hilbert-Schmidt inner product. So what do you think that's going to be? That's going to be to do this to this guy instead.
Right. Comma the bar A.
Bar A, yep. Okay, so that's my definition of vertical double dagger. Okay. The Hilbert-Schmidt inner product, or Hilbert-Schmidt adjoint. Hilbert. Does anybody know if the Schmidt of Hilbert-Schmidt is the same as the Schmidt of Gram-Schmidt?
It is. No.
There's a few Schmidts.
I think so.
I think so, yeah. It just occurred to me recently. I'm like, oh gosh. Yeah.
So
Yeah.
incidentally, because
Inner
that I would consider what you just defined as the standard notion of adjoint of a superoperator in the field of form information, where it is typically denoted by just the dagger.
Just the dagger, yeah. And I hope you'll allow me to use double dagger.
That's fine.
Because otherwise, yeah, using a lot of daggers. And
I think you were trying to define Hilbert-Schmidt adjoint. An inner product is defined on the left of the
Thank you, thank you. Yeah, I was just telling you about how there's these different ways to contract superoperators. So there's actually another adjoint around too. So like CP-TP maps are Hermitian under a dual adjoint. And so because of that, there's actually two superoperator adjoints where you can start doing stuff. And so Carl and I use vertical double dagger and horizontal double dagger. And so there's a other side to it. If you think about how this interacts with Choi-Jamiolkowski, there's this other adjoint, superoperator adjoint, and they both need names. So I'm just explaining my madness.
If I decide to write everything, every superoperator is a matrix on the vector space of Hermitian operators. So like the Choi matrix representation of that superoperator.
Yeah.
Then, that matrix has a kind of transpose, complex conjugation and transpose, which we know
Sure.
of that joint.
Yeah.
Is the two things you're talking about just this transpose versus?
Yeah, so what do you call the map from the process matrix to the Choi matrix? Do you have a name for that? Carl calls it the sharp. Yeah.
Okay.
Yeah.
I don't think.
So there's two different ways to think of
Oh,
a superoperator as a matrix. Two different ways. And this one looks just like Hermitian conjugation in the one way, but then it looks different in the Choi way. And so that has a name, or that's a thing. Carl and I call this sharp. And then the point is, if you think of the hyperoperator, sharp, which takes the process matrix to the Choi matrix, and then you dagger that, and then you come back. Okay, that's what we call the other adjoint. And so statements like Z is CP become that they're self-adjoint under this dagger.
hang on a sec. That equation you wrote to the left.
Yeah.
The sharp took you into the space of matrices.
The sharp,
Takes you
so like what the sharp,
CP maps to matrices. Is
so like in one basis, okay. I'm going to say one more thing and then maybe we should move on.
Okay.
All right. So if you like write everything in this basis, okay, so we're digging in. Very quantum, the sharp is very quantum. We're not using the sharp in the stuff I'm doing right now, but it will be used soon. So this thing sharp is just swap B and D. Okay. And this is more natural than what Choi did because you don't have to worry about complex conjugations and bending the identity, and, right? Because it's very natural to swap two bras. Okay, but this is what the sharp is. It looks the simplest in this basis.
Yeah, okay. It's clearly, in some representation, it's just the transpose, so I'm just not clear on.
Oh, well, no,
if I take that CP map you just defined, think of it as a matrix acting on the helper space.
oh gosh, you want to think about this one?
No,
Oh.
just here, what you wrote. Out of
This one I just defined. Okay.
that one.
Okay.
If I rewrite that as a matrix acting on the vector space of Hermitian operators.
Acting by putting it in here, or
I mean,
yeah.
like,
Yeah.
what kind of space does this thing act on? Answer: it acts not only on density operators, but I can act it on any Hermitian operator.
Yes, but it can act in
Hermitian operators
two ways.
are closed under linear combinations with reals. Therefore, the set Hermitian operators form a vector space. I can make it an inner product space with the Hilbert-Schmidt inner product. So I can think of this, if I like, because it's a linear map, as a matrix acting on the vector space of Hermitian
Yes.
operators.
Yeah.
If I take that matrix representation and I just take its transpose, I think that is equivalent to your sharp.
Maybe. Yeah. The way where there's a divergence. So when you said this thing acts on a Hermitian operator, there's two ways this can act. Okay. A Hermitian operator has one bra, one ket, right? And so you could plug those into these two. That's a bra and a ket that can contract. And so that's not the one you're thinking of.
No, the Hermitian operator is called X. You just put X with it.
You would put it in here, yeah.
That's natural action.
So that's yeah, and that's what that matrix I would call the process matrix.
Okay. Yeah.
But if you acted it this way, you contract this against the Hermitian operator, then that's the Choi matrix. Yeah. So,
Okay, that's
which is the same.
You can point to the right-hand side of your equation.
Okay, yeah, exactly. That's what this sharp is doing.
Sure, there's
it's
certainly
toggling.
a difference of transpose between the Choi isomorphism
Yep.
and the Jablonski isomorphism.
Yep. Yep.
It seems to me your sharp is, in the language of process matrices, just the transpose.
Maybe. Yeah. I think of it, it's got a complex conjugation in it too. So the assumption is if there's a number here, it would get starred. So, yeah. And that's part of what I was saying about this being natural, swapping two bras. While I think the original Choi, because it's so matrix-based, it's usually phrased in a way that has to swap a ket and a bra. And that's not as natural. But I'm just speaking from memory. Okay.
Yeah, why don't you go on?
Yeah.
Maybe we can come back to it when it shows up later.
Yeah, so indeed superoperators are crazy. We'll return to this when, like I said, we're not going to use this second action in Krauss operator world. But when we move to frame operators, then there's this other action. And then everything really comes together then. So yeah, for now, there's just the one. Okay. So I'm going to erase these guys. Okay, so then the main thing to conclude from this, I'm just going to say it then. So B dagger, oh God, I actually have to do it because I get it wrong every time if I try to say it from memory. Okay, so consider Z equal to C O dot D dagger. Okay. Then what does this say? It says B C O dot D dagger of A, or z double dagger of A. What is that? That's B, z of B, A. And that is C O dot, C B D dagger, A. And that is, by the cyclic properties of the trace, B, C dagger. Oh, yeah, that's right. Okay, good. Okay. So, in other words, right, Z or C O dot D dagger double dagger is C dagger O dot D. Okay. So that's the crucial thing we're going to need to show this guy. Okay. Are there any questions? So like this is a place where it helps me to use daggers and double daggers. Yeah. Just to keep track of what's an operator and a super operator. Okay. So Carl and I call this dagger in place, vertical dagger. So you don't swap these or anything. These guys stay put, but they get daggered. Phew! Gosh, I'm so sorry. I didn't realize I needed this to show the trace preserving property, but I did.
So maybe I'll make a comment on this that
Yeah.
in the quantum information literature, the place where the dagger of superoperators comes up is sort of switching from Heisenberg picture to Schrodinger picture and back again.
Is that right?
Yeah, because if you're talking about evolution in terms of CP maps.
Oh, you mean acting on the state versus the observable.
Moving states forward, let me move the backward. It's the dagger of the CP map that acts on the effects. And in that context, if C and D are cross operators in a cross decomposition, that's sort of familiar that the dagger of the super operator should swap.
Yeah, exactly.
Which term the dagger of the cross operators?
Yeah, exactly. So like a main consequence of this, right, is when I write 1 omega x O dot omega x dagger, right, this is just supposed to be the POVM element. Yeah. Ends up wrapping around the other way. Yep. Hi. Okay. That's my second advisor. I was like, oh, God. Okay. All right. So hopefully that feels a little more familiar. Okay. So now, we'll just do this guy. So what is add? So add x is self-adjoint for x Hermitian. Everybody sees that if all we're doing is daggering in place. And remember, add x I'll just write it out. Okay, by definition, right, this is just x O dot 1 minus 1 O dot x double dagger, right? And this is linear, and these are Hermitian. So that's just add x. And indeed, the key property of the identity is it commutes with everything. So indeed, add x double dagger of 1 is 0. Okay. So therefore, 1 add x is 0. Okay. As I said, those are the same statement. Okay. All right, so then...
Yeah, we're doing x is Hermitian, yes.
Yeah, exactly. Okay, therefore, 1 e to the minus half theta add x squared, right, is 1. Okay. So that shows that indeed the channel is trace preserving because it leaves the identity invariant. Yeah. So we didn't need the spectral properties of the trace. We just needed that cyclic property. Yeah.
I have a very trivial question, which is why have you introduced a notation, act from the right without the double dagger as a kind of synonym for act from the left with the double dagger? Is that going to be important later on? Because in the context of the current discussion, it hasn't done anything for us. It's just a new notation for something that we have a notation for. So why? Why is it there?
Yeah, thank you for asking, because at this point it is out of habit because of the other stuff I do. Yeah, so it's just out of habit, this. Let's see. Like, if you probably, in matrix language, trace preserving, that means you have ones and all zeros in either the first column or the first row. That doesn't help, because this is not how I think about it. I'm just trying to think of what this is the same as. So never mind.
It would confuse me a bit is that there's a natural place for a kind of right action to appear. If you're leaning into this rounded direct notation, then we're very accustomed to right action of an operator on a bra should be thought of as the dagger of its left action on a ket. But here you're not using direct notation, so I don't know why we're sort of introducing a right multiplication notation.
Yeah.
It just seems to me you'd be better off writing add double dagger acting on identity is 0, period.
Sure. Yeah. Okay. Yeah. I understand. So yeah, just to repeat what Rob is saying, basically we could have gotten where we needed to go if I just didn't say this and then go back to it. Yeah. Absolutely. Yeah. So is everybody happy though with the statement that we've shown that Z is trace preserving? Okay. Even if this beginning and end didn't seem to do anything. Yeah. Alrighty. So I guess just to be a little clearer though, this also tells us what the POVM elements are, right? So if I applied all of the selective operations.
Chris, did you mention, just in case anyone's confused, that trace preservation, which is usually thought of in the Schrodinger picture, in the Heisenberg picture, the adjoint of the map acting on identity is the identity. Unital of the unitality of the adjoint is the same as trace preservation. That's gone by already.
Okay, yeah, so to bring it back to this square, this is what you probably think of as trace preserving, is the trace of the thing on row is the same as the trace of row for any row.
Right.
Okay, and that's why we can then just drop row, is because then all that matters is how Z acts, how the adjoint of Z acts on the identity. Okay, and we just showed that the adjoint of Z leaves the identity, and so maybe
clearer than the equation below would have been. So if you write that for all row in that box.
For all row.
And then below it, I think a clear equation would be Z double dagger of identity is equal to identity, which is what you've now proven over here. Like that is.
Yes.
It's nice if row drops out of it, and it's. You see what I mean?
Okay. You're saying. I think I do.
Double dagger of identity is equal to identity. That's the equation, which is the equivalent.
Oh, that's not on the board. I see. Okay. So.
What you you've ultimately
Yep.
proven therefore.
Yep, thank you, absolutely. So TP definition, number 1, and then TP definition, yeah, yeah. Number 2, Z double dagger of the identity is the identity. Okay. Great. Yeah, sorry, I didn't prepare this part. Okay. All right, so good. So the POVM, that's then just, oops, no, that's right. Right, in this case, because in fact this Gaussian measurement we started off with is Hermitian, it has Hermitian Krauss operators, then you can call it Lüders. Okay? Then it's very easy to calculate if you know omega, what omega dagger omega is, right? You just lop off the square root here and put a couple of 2's. Okay? So in fact, I'm not going to bother writing that. But the point is that the completeness relation is universal. We didn't need any Hilbert space or spectral information to establish the completeness relation. Okay. I'll get more and more detailed about what universal means as the weeks go by. This is the first taste. Okay, are there any other questions or comments? Let's see, we've got another half hour. Good. Great, so now we're going to go through a couple other Gaussian channels, or Gaussian instruments, excuse me. Okay. So now I'm going to consider a different system-meter interaction. Okay. I'm going to consider, okay, let me give this a title. I've been asked to be a little more structured. Okay, so what am I going to call this? Oh yeah, okay, we'll just call this random unitaries. Gaussian random unitaries. Okay, so the whole setup is the same except that I'm going to change the interaction to be. So I guess I'll put a prime on this guy to emphasize I'm changing it. So now, instead of displacing the meter, depending on the observable, so I'm going to now call the observable y, because pretty soon I'm going to do both this and the original interaction. So I'm just changing the name of the observable. What used to be called x, I'm just now calling y. And instead of displacing the meter, I'm going to boost it. Okay, so what does boost mean? It means I'm using the quadrature q as the meter observable. Okay. Does everybody see why I call it boost? You can think of this as a translation in the momentum. Okay. So that would be a Galilean boost. Okay. So then I'm just going to say the answer. Right? So what changes is instead you get, for the Krauss operator, so you get this same distribution because the meter wave function is the same. But then you just get now a random unitary. Okay? So does everybody see that? If I change the interaction to this guy, now the Krauss operator is not Luther's, it's unitary. Okay. Yep.
Sorry, no, I don't see that.
Yeah, remember this guy, by definition, was root dx, position measurement, let me put a prime, he's different. This interaction, I cannot make up my mind about my u's. And then this Gaussian meter state. Okay. So point is this QM sees the position measurement. And okay, so then this guy is just the initial wave function. This guy, the QM, just turns into the register of the position measurement. Okay. Okay. And then we could go through the calculation. It's actually pretty simple. I'll try to just communicate it. The first thing that's really obvious, right, is that, okay. So once you have the instrument, there's basically two secondary objects to calculate, right? The channel and the POVM elements. And pretty clear, right? All of the POVM elements are proportional to the identity. Okay. So they just are the distribution, and there's zero sensitivity. Okay, and then just identity of the system. All right, Krauss operators are unitary. On the other hand, the decoherence channel looks exactly the same. Okay. Okay. And I think the quick way to see that, right, is, so this thing becomes this O dot itself dagger, right? And so because this is unitary, that dagger introduces a minus sign, right? And so that's how this thing turns into an edge. Okay. So there's an important moral here, right, which is decoherence and measurement are not the same thing. Or I would not call this a measurement, right? I would call this a non-measuring interaction, but it produces exactly the same decoherence as a Gaussian measurement. So, like if you have the channel and you're measuring that your information is dissolving or decohering, you don't know if it's decohering because of random unitary interactions or some eavesdropper. Okay, so you don't know what the instrument is, but if you find that your channel is this, right, it could be that the instrument is this Luther's guy. And that would be the worst case scenario.
Maybe a useful way of thinking about it for others is that I see this and I think, all right, clearly there's decoherence because information about the Y observable is being imprinted on the meter in the momentum basis. It's boosting by an amount that depends on Y. Now,
it would be in the momentum basis, right?
Had the meter been prepared in a momentum state and then measured in the momentum basis, you would have learned things and not had a trivial POVM. But because you are preparing in a position, eigenstate and measuring position, none of that information that's been encoded in the meter is becoming accessible to you. So decoherence has happened, can't avoid that, and you're just not learning anything about the system. You've chosen a mutually unbiased basis to measure to the one in which the system was encoded, so you learn nothing about it. Same decoherence, but no non-triviality of the measurement informativeness.
Okay. Okay.
Yes?
Yeah, I think I agree with that. And yeah, it's just a little different. So maybe to bounce back a little bit. So yeah, like what Rob was saying, you could have changed, because this is just my style, you could have changed that position measurement to a momentum measurement. But I do think in these Gaussian meter cases.
To a preparation of a momentum eigenstate. That would also be.
That's actually, no. It's very important that the Gaussian meter state is a Gaussian state. So the meter preparation is never a position or momentum eigenstate. Those don't exist. Okay.
Oh, I see. That's zero.
Yeah, is a Gaussian. Yeah.
That's very confusing because you use the same notation for that as you do for your position eigenstates. So
Right. Yeah, I did. It is confusing. I understand. But indeed, 0 meter does not equal the x equals 0.
Okay.
Yeah.
But it is not spread out in either position momentum, so it can give you information about translations of position or boosts in momentum if you measure that basically.
Yeah.
Okay.
Yeah. And
I interrupted you. Why don't you say what you were going to say?
thank you. I guess one thing is, so the Gaussian state is symmetric under certain kinds of rotations. Okay, so that's in fact the way to understand that I could have just stuck in the appropriate rotation. I'm going to call it F for rotate position into momentum. And then if I pass that through here, then this will write things in the language Rob was saying, which is if I pass this through here, then what I have is the same interaction I had before, but then I'm changing the measurement. Yep. Indeed. So there's always those two ways to think. But because I'm about to talk about generalized Gaussian instruments, both x's and y's, I like to keep the meter unchanging. The final meter measurement unchanging. The bra. Yeah. Are there any other questions or comments? Okay. Yeah.
Can you explain a bit more the intuition behind why the decoherence channel is different, even though in one case,
The decoherence channel is not different.
it's not why they are not different?
Do you want a calculational explanation or?
Like maybe the physical intuition.
Yeah, random unitaries also cause decoherence. Yeah.
And somehow they cause decoherence in the same basis, because in both cases, if I write y equals to the x, then they're exactly the same.
Yeah.
And this is because in the same case, in both cases, it's the information about the same basis that is being kind of spread to the meter. So it doesn't matter what you measure afterwards, the fact that the interaction is this.
Okay. Oh, okay.
I
Okay.
don't know.
Well, that sounds like what Rob was saying. You can think of this as the terminal measurement isn't taking advantage of the information that is there. So indeed, sort of that information is still leaking out of the system. It's just not being read properly. Right? And so if you don't measure in the right basis, you don't see the information. But the registers are still happening, and they still decohere. They randomly boost the system. Yeah. Yeah, definitely from my side. I'm more mathy than I am narrative. So, yeah, I think Rob was like precisely, you sounded like Rob for a moment. Yeah. Okay. Yeah. Are you any happier with how I put it? I mean, yeah.
I guess also, so it's the fact that in the end we do this non-selective kind of measurement, because we sum over whatever you measure in the momentum position.
Yeah, if you don't know X, you don't know X. Yeah. And yeah, somehow the effect is exactly the same. Yeah. Okay. Whew. So where are we? 15 more minutes. Okay, so now we're going to start talking about sequential measurement. So, yeah, this is a good board to do it. So what is a sequential measurement? I mean, you can probably guess, right? If a box refers to the same instrument, right, I don't have to measure this thing once, right? I could apply the instrument, get a register, and do it again. Right. And what's the output state, right? The output state is you just keep compounding these cross operators. Oops, dagger, dagger. I got X and dagger. Okay. Okay. Everybody see that? We got one nod. Do you guys see it? You got nods. Good. All right. So I'm going to define the free product. So, because formally, this can be very helpful. I don't know if it's helpful immediately. You guys tell me. Okay. So I'm going to put, right, the second measurement is always going to be on the left. And these don't have to be the same instrument. Again, I'm only considering Krauss rank 1 instruments. Okay? But the free product is just going to be exactly what I'm saying here. Right? It's just going to be the set of all products. Okay? So to say this a little better, definition. The free product of B and A, right, is the set of BA. You need to know how to multiply them, right? This isn't defined for just sets, right? BA needs to make sense. But the set of BA is such that B is from B and A is from A. Okay? Okay. So the free product is the most basic structure of sequential measurement. Okay? Are there any questions yet? The reason this is an asterisk is because of the relationship to convolution. Functions, convolutions of functions. Yeah.
Wait 2 seconds. What did he call this product?
The free product.
Okay.
Yeah. It's called free because in group theory, the point is you don't have any way to contract this. You can't. So I haven't given you any structure. I haven't recognized any structure that would be able to say, for example, so, if I did this measurement once and I got X and Y, or if I did this measurement twice and got X and Y prime, okay, a good question to ask is, are those the same total Krauss operator, right? And you don't know with the free product. So free means free of constraint, okay? Because this is a constraint, anything that would identify two different products, right? So it's called free because it's free of constraint. Okay. Any other questions? Okay. So then next thing to notice is if I say the channel of an instrument, this is where my notation starts to get a little You guys just tell me if you're okay. So I think this is fine. Okay, so I'm going to say the channel of an instrument is just the sum of all the selective operations. Okay. Then it's pretty easy to see, right, that the channel of a free product is just the composition of their individual channels. Okay. Do you guys want to see the motions? Are you happy? You're happy? Okay, I got 2 nods. Speak now or forever hold your peace. Okay, great. So in particular, right, that means if I do measurement n times, okay, so now this just means I star I n times, okay, that's just composing the channel with itself n times, okay, that's just this thing applied n times, okay. So in particular, what does that mean about the Gaussian instrument, right? So now, if I is a Gaussian instrument, okay, need to be more organized. So, if I is Gaussian, that means that the measurement done n times is what we've calculated a few times now, but with a n, right? Okay, nothing too crazy. But now this is where it's kind of crazy. So if you count time in terms of these measurements, right, if t is the time of this measurement, then the structure is such that this takes twice the time. Okay, you do it again, it's going to take as much time. Do it again, it takes n times the time of doing it once. That means, so if t is the time to do I, then theta is actually the square root of the time. So there's some constant, okay, for some, and this constant is going to have units of inverse time, okay, and it's called the measurement rate, called, for some k, called the measurement rate. All right. So Marina was just asking me before class about the Zeno effect, because we're about to talk about continual monitoring. So indeed, I'm going to take the limit t goes to 0. But because I'm going to take the limit t goes to 0 this way, there's no Zeno effect. Okay? And this is a property of diffusive measurement. Okay? So that theta is square root of the time. And this is the beginning of a whole world of analysis. Yeah.
I'm a bit lost.
Yeah.
So the n with this discrete n-fold repetition.
Yep. Yeah.
And it's sort of, I was sort of imagining that, you know, that sort of increases linearly with time.
Mm-hmm.
But
Yep. And that means theta squared is time. Yeah.
I do not understand why there's an implication
Okay.
about how to interpret n and the interpretation of theta. So when you say and that means that theta must decrease, theta squared must decrease linearly with time. How does that follow from n being? Are you saying that you want that exponent to be n times the time it takes to do I? Is that sort of the constraint?
Yeah, exactly. Yeah.
Why? Why do you want it to have that form?
Well, that's
Because you want it to be total time up there in the exponent. Like this is the
yeah.
n theta squared boxed should be the total time that has elapsed.
Exactly.
Okay.
Yeah.
And now why should it be the total time that has elapsed?
That's, I guess, the assumption that these are independent,
Okay.
and if I just do it again, I can do it again immediately. And so every time I apply a box, it is a factor of time. And yeah.
Is this box stuff a kind of cartoon that really what we're imagining is a kind of continuous variable x of t, where I get a kind of trace over time that's continuous, like this is the outcome at every moment in time, rather than a discrete sequence x1, x2, x3? That's what I have to imagine.
I'm not thinking of tracing over time. What was that?
But sometimes people use the word trace to mean just a continuous
Oh,
function. which-
sure. Yeah, absolutely. That's what's about to happen. So yeah, we're about to take t to 0. Exactly. So indeed, for now, it's just boxy because I thought it would be easier to step into it that way for you guys.
Okay.
But yeah, we're about to take time to 0. Yep. In which case, this starts to look like the stock market. Yep. Brownian motion. Okay. Okay, so we've got 5 more minutes. I think I'd like to introduce you guys to the Wiener increment.
Sorry, guys.
Yeah.
Like, why? Like you're making a measurement, and then you're making a measurement
Again.
right after, again. But that's not that does not give you the Zeno effect.
Right.
Say it again.
It's because you're putting the clock over here. Yeah, theta squared is theta squared, right? And if time is theta, then you get Zeno.
But why?
Oh, if you take t to 0, then you have t squared factors that don't do anything. Yeah, but if time is at the level of theta squared, which it is for cross sections and decay rates, and in this case, then the interaction actually goes to 0 as the square root of time. Yeah. So I think of the time as like attached to the observer, and so if the observer is over here watching the stock market, it's just a different scale of time than if you say the unitary strength is the time. So what's missing? I don't think a lot about Zeno. I just think this theta squared. Either theta squared is time squared, and I'm calling that Zeno, or theta squared is time, and that's a Markov process. Yeah.
Okay.
Yeah. These sequential structures, and they're very different. Yeah. Yeah. All right. Okay. So yeah, let me introduce you guys to the Wiener increment. So going back to, so I just showed that if you're interested in sequential measurement, that actually theta goes as the square root of time. So that actually means that if we consider a weak Gaussian, instrument. So I'm going to just write the Lüders one down first. Right? Then what was omega x? Right, omega x is dx over square root 2 pi sigma squared e to the minus x squared over 2 sigma squared e to the x over sigma, but now we've got this root kappa dt here, observable x minus kappa dt. Okay. Okay, so this is the same expression I started today off with, except I've replaced theta squared for kappa dt. Okay. Okay. So this random variable, x over sigma square root of dt, okay, has a special name. It's called a Wiener increment. Okay. And of course, we're going to start doing these in sequence or continually. So then the picture is going to become, right, that each one of these dWs actually gets a time. dt, etc. Okay. And one of the craziest features about these dWs is that they're not ballistic, right? When you integrate, so if you actually like plot wt, and we'll talk more about this, I just want to give you a picture in your head. So if you actually plot wt, the integral of this as a function of time, you actually don't have something differentiable. Okay. It looks like the stock market. This is my best random. I know it's not very random if you Fourier transform it, but random enough. Okay. All right. Yeah, the history of the Wiener increment is crazy. So this is what's called a Wiener process. It's also called a diffusive process. It's also called Brownian motion. Okay. It's actually a real trip how much this motion has a vision of automata, of machines and beings. One of the last books Wiener wrote was The Human Use of Human Beings. There's a lot there. So like diffusive is like pictures, visions that Fourier would have had when he was doing the heat equation. Okay. Brownian is like Einstein 1905. Well, this is one of his miracle papers. But then Wiener is the one who started building autonomous machines based on this idea. Yeah. So that probably sounds woo-woo if you're not initiated, but it's true. There's something crazy to realize when you really look at this random motion. You see something that all of the primordial information scientists were talking about. Automata is a very outdated term, and yeah. Anyway, so I introduced you to the Wiener increment. And so we're very close to talking about diffusive measurement. So I guess on Thursday, we will start with that. Okay.
Thanks.
Are there any questions? Wiener increment.
I just want to follow up on Marina's question about
Zeno.
how this is connecting to Zeno.
Yeah.
So while looking at that, I thought if theta is linear to 1 over n, then this is
Zeno.
Zeno.
Yeah,
But
yeah.
in your case, you are not.
It's not. Yeah, this is root dt. And that makes all the difference.
It's irrelevant to what n is, actually.
No, I wouldn't say that.
How is dt actually? Is n has anything to do with the n that you choose over there has anything to do with theta or dt or?
Yeah, again, what we're going to do with these is repeat the instrument. And so that says, do you add thetas or do you add theta squares? Right, and if this represents the element of a repeated measurement, then you add theta squares.
Okay, so then n is just some number of.
Is my way
Okay.
of talking about the addition rule. Yeah, yeah. Okay. Are there any other questions or comments? Thank you guys for coming.